Okay, so in this video we're going to be talking about constructing Born-Haber cycles and carrying out calculations in order to calculate lattice enthalpy. And to begin with, I want to recap the term standard enthalpy of atomization, which we looked at last lesson. It's the enthalpy change that accompanies the formation of 1 mole of gaseous atoms from an element in its standard state under standard conditions. So I've got an example here of an enthalpy of atomization. And you'll notice in the definition here it says the formation of 1 mole of gaseous atoms. So in order to balance this equation to produce 1 mole of gaseous atoms, I've had to show it as half of a chlorine molecule. And you can see here it has an enthalpy change of atomization of 122 kilojoules per mole. And it's a positive sign on that, showing us that it's endothermic, which makes sense because you'll have to put in energy for this molecule to undergo that homolytic fission and break the bond, so you've only got gaseous atoms. However, if you wanted to form 2 atoms of that particular substance, 2 gaseous atoms, then all you would need to do is double the enthalpy of atomization to form 2 atoms, as we've seen in the product here. And you'll notice that that takes a whole molecule of chlorine to do so. Let's have a look for oxygen now. So oxygen's enthalpy change of atomization to produce 1 atom is plus 248 kilojoules per mole. But again, if we wanted to produce 2 atoms of oxygen, then we'd use a whole molecule of oxygen like this, and then we would just simply double the enthalpy change of atomization in order to get those 2 atoms. Now, quite often in the Born-Haber cycle tables of data that they give you, they will either give you an enthalpy change of atomization, or they might give you a mean bond enthalpy, or they might call it a bond dissociation enthalpy. And this is a little bit different to the enthalpy change of atomization, so you need to be prepared to use these numbers. So the bond dissociation enthalpy is the enthalpy change when 1 mole of covalent bonds are broken to form gaseous atoms. And remember that this value here is a mean because it's averaged for that particular bond over a range of different compounds. So this would be an example of a bond dissociation enthalpy. And if you compare this with atomization enthalpy, you'll notice that it's producing 2 atoms. Right, why is that? Well, if we were to look at chlorine, well, there's only 1 covalent bond in chlorine. So if you were to break a mole of covalent bonds, then inherently you'd end up with the 2 atoms either side of that covalent bond. You'll also notice that this number is straight away double the atomization. Well, that makes sense because it's the same essential equation as we showed here when we wanted to form 2 atoms. So therefore, if you're given a bond dissociation enthalpy, but you only need 1 atom in order to complete your Born-Haber cycle, then you would actually need to halve the bond dissociation enthalpy, or the mean bond enthalpy. You'd need to halve it. So just to summarize here, atomization produces 1 atom. So if you're producing more than 1 atom, you need to multiply it by whatever that is. Whereas bond dissociation will always form 2 atoms through the fact that you're breaking a bond, and you'll end up with what's either side of it. So if you want just 1 atom, you'd need to halve it. Another example over here would be oxygen. So the bond dissociation enthalpy of this would inherently produce 2 atoms of oxygen because you're breaking 1 of the double bond between the oxygens here, which means you'd end up with 2 atoms of it. So again, if your Born-Haber cycle only needed 1 oxygen atom in order to complete it, such as magnesium oxide or calcium oxide, like a group 2 oxide there where you've got a 1-to-1 ratio, then you would need to halve this value for mean bond enthalpy in order to get the correct value there. So make sure you pay particular attention to whether you're looking at a mean bond enthalpy or bond dissociation enthalpy, or whether you're looking at a standard enthalpy change of atomization, because this is going to affect what you need to do with the values in order to complete your calculations. Okay then, so let's have a look at some exam questions which involve Born-Haber cycles. And these calculations and completing these Born-Haber cycles are the kind of thing that you can only get good at once you've done loads of them. And it's a very important point to make that you should also be doing these in the days before your exam quite frequently, because they're very easy to make mistakes on and lose that technique. So to begin with, we're provided with a question which asks us to to complete this diagram of a Born-Haber cycle. So we need to look at what's going on already and then consider what changes we can make to it. So to begin with, we've got magnesium oxide as a solid, and this is the solid ionic lattice form of it. And you can see over here we've got the elements in their standard states, and we've got the half in front of the oxygen here so that it balances to form 1 mole of that ionic compound. So actually this change that you see here is the enthalpy of formation of magnesium oxide. Okay, so that's a standard enthalpy change of formation where 1 mole of a compound is formed from its elements in their standard states, all under standard conditions. Now if we have a look at this change that's going on here, okay, well you can see that the oxygen no longer has this half in front of it, and you've just got atoms of oxygen now. So actually what this represents here is the standard enthalpy change of atomization of oxygen. However, the value they've given you in the table over here is the bond dissociation enthalpy for oxygen. Now if I just get my pen here to show you what this represents, well the bond dissociation enthalpy for oxygen says that you're going to break 1 mole of covalent bonds. Now if you were to break this 1 mole of covalent bonds between 2 oxygen atoms, then you'd actually end up with 2 oxygen atoms. Whereas if we now look overall back at the equation that we've shown, well we're only forming 1 oxygen atom. So this 496 value here, well that refers to forming 2 oxygen atoms. If you break a bond, you form 2 products. So what we would need to do with this value here before we use it in any kind of calculation is we'd need to halve it, right, to form 1 oxygen atom. Okay, so let's go back and look at it again. So the change that's occurred here, okay, you can see the magnesium's gone from a solid to a gas. Now when it's in a solid form, it has all of its strong metallic bonds caused by electrostatic attraction between positive metal ions and delocalized electrons, whereas when it's in the gaseous form, it doesn't have any of those bonds. So that's the atomization of magnesium, going from its standard state to gaseous atoms, okay? So what we can see then, let's just track those changes that have occurred so far. So we've got the enthalpy change of formation of magnesium oxide, which is minus 602. Okay, then we've got the bond dissociation enthalpy for oxygen, which is plus 496. But remember, we had to divide that by 2 to make it equivalent to the atomization enthalpy there. Then we've got the atomization of magnesium, which was plus 150. Okay. And then finally, we've got another change going on here. So once you've carried out all of your atomization, which is essentially what's going on here. Okay, so that was our atomization. Once you've carried out your atomization, what you're going to need to do is change those atoms into ions, because ultimately you're forming an ionic compound, and ionic compounds, the formation of which involves the transfer of electrons. Now, the transfer of electrons always occurs from the metal, because the metal is oxidized by losing electrons, to the non-metal, because the non-metal is reduced by gaining electrons. So therefore, in terms of the order in which we need to do this, well, we need those electrons ready and removed from the metal first so that they can be transferred to the non-metal. So we always need to carry out oxidation first. So therefore, we're going to need to do these first ionization energies of magnesium and the second ionization energy of magnesium in those 2 stages before we were able to do the electron affinity on oxygen. Remember, ionization energy refers to oxidation and electron affinity refers to reduction. Okay, so what I'm going to do then is I'm going to need to now oxidize the magnesium, and I'm going to need to do that in stages. So the first oxidation would take magnesium from being gaseous atoms to magnesium 1 plus gaseous ions, okay, like that. And because it's lost an electron, I need to show that electron that's been lost, like that. Okay, the oxygen wouldn't have changed yet. It doesn't immediately transfer over to the oxygen. And it's important that we don't do that, because if we immediately transferred it, then we'd be basically adding up all of these energy changes in a singular step. And if you wanted to work out one individual step, you'd remove your ability to do so. So next up, we've got to carry out the second oxidation of magnesium, or the second ionization energy, and that has a different energy value associated with it. Remember that the second ionization is always more endothermic than the first, because you're removing an electron from an already positively charged ion, so you've got to overcome more attraction there. Now, I'm now going to say that there's 2 electrons. There's only been a change of 1 electron between this and its previous row. However, we're kind of adding that electron onto the one that was already there. plus oxygen as a gas. Haven't really got enough room with this pen to draw it on there, but never mind. Okay, so we've given state symbols for everything as we go, and we've shown now the first and the second ionisation energy of magnesium. So let's associate some energy changes with that. So the first was plus 736, and the second ionisation energy was plus 1450. So now that we've ionised the magnesium into its 2+ ion, we've got those 2 electrons, let me just show you here, we've got those 2 electrons available to actually be able to reduce the oxygen. But again, we need to do this in stages. So what I'm going to do to start with is carry out the first electron affinity of oxygen. So the first electron affinity would make a 1- ion. So I'm still going to have my Mg2+ gaseous ions. If I use up one of those 2 electrons, I've only got one left because the other one was put onto the oxygen like that. Okay, so that's my first electron affinity for oxygen. Remember that that first electron going in is actually exothermic because it's quite attracted to the nucleus. Whereas the second electron affinity will be endothermic because you've got to overcome repulsion to push an electron into an already negatively charged ion. So we can see now that this second electron, let me just show you my laser again. There we go. So this leftover electron has now gone on to the oxygen over here, which is why it's no longer shown on this row. So that would be equivalent, this arrow here, to my second electron affinity for oxygen. So the energy value that I've got associated with this particular one is plus 844. Now finally, what I need to do is use these values that I've placed onto my Born-Haber cycle, as well as the equations, to calculate this value here. Now this value here is going down, and it's going from the gaseous ions to the solid ionic compound. So this value here is called the lattice enthalpy of formation, or the enthalpy of lattice formation, which is what we're asked to calculate in this particular question. So this is the energy released when those bonds are made, right? So BMX, bond making, is exothermic, hence the reason the arrow is going down. You're making bonds between these gaseous ions, allowing that electrostatic attraction to take place, and in doing so forming the solid ionic compound and releasing a whole load of energy in the process. And we want to calculate what that value is. So what we need to do is recognise now our roots, okay? So what I'm going to do is change my pen colour quickly. So this first root, if we go from, where am I? Here we go. If we start here, we make this our starting point, the elements in their standard states. Always try and make that your starting point. Well, we want to go from there to our product. So we're going from the elements in their standard states to our product. Well, we can call that root 1. Alternatively, if we go from this same starting point, but we try and get to our product another way, then we've got to go all the way up here, round, back up again, and down here, and then we'll finish at the same point, right? We'll finish at that magnesium oxide solid. So we can call that root 2. And one of the things you need to know about any of these kind of cycles, whenever you start and finish at the same place but follow 2 different routes, this is Hess's law, the enthalpy change is independent of the route taken, well, root 1 is equal to root 2. So we need to be able to work out part of root 2. So basically, if we say that root 1 is equal to the whole part of root 2 that we know, so we know root 2 up until this point here, right? But we don't know this point of it here, the lattice enthalpy. Okay, so we can say that root 1 is equal to root 2 that we know plus that lattice enthalpy. That makes sense. I'm just saying the whole of that blue line there, really, but I'm splitting that blue line into 2 parts. This first part before the big line over here being the root 2 that we know, and this bit down here being the lattice enthalpy. Well, that's the same as the previous equation. So therefore, in order to work out the lattice enthalpy, we can say that the lattice enthalpy is equal to the root 1 that we know minus the bit of the root 2 that we already know. Okay, and that will give us our lattice enthalpy. So let's now explain this mathematically. This lattice enthalpy, delta H LE, is going to be equal to minus 602, that bit of root 1, or the whole of root 1, minus, now we'll put this in brackets. Well, let's just put the numbers in for the part of root 2 that we know. Plus 496 over 2, so I'll put that in another bracket here, 496 over 2, plus 150, plus 736, plus 1450, minus 142, so we're just doing the sum of all these and that's equivalent, plus 844. Close brackets. Okay, now when I type that into my calculator, and make sure you type it in carefully, I get an answer here of minus 3,888. Right, quick check. Does that number that we've just calculated make any sense? Well, it's a negative value, and this arrow for lattice enthalpy is pointing down. So it's exothermic, which is what we would expect for bond making, right? Bond making between the gaseous ions to form the solid ionic compound. Bond making almost always releases energy. So that negative value makes sense. Also, you can see of the values here, this is a particularly large arrow, so we should have a relatively large number. So this number looks reasonable to me. I have checked it against the mark scheme, and it does work. Okay, so that's how we calculate lattice enthalpy of formation. Now let's have a look at another example. Okay, so question 2 is all about sodium fluoride this time, and we're asked to complete the Born-Haber cycle for sodium fluoride by adding in the missing species on the lines. So the shape of this Born-Haber cycle looks a little bit different, but it's not majorly different. So we've got the solid ionic compound over here, and we've got the elements in their standard states, again balanced to give 1 mole of that particular product. So this enthalpy change that we're looking at here is the enthalpy change of formation. However, this time in the table, they've not given us names of each of these enthalpy changes. They've actually given us equations for each of the enthalpy changes. Well, let's have a look at what happens on this line to this line. Elements in their standard states to 1 mole of the ionic compound. That's a standard enthalpy change of formation, and the value's given here. So I now know that this value is the enthalpy change of formation. Just change back to red quickly. So I know that this value here is my minus 569 value. Okay. Now, in order to move on, what we're going to need to do is atomize both of the elements that you see in this row here. We've got to first break the bonds, and then we can carry out ionization. Now, it doesn't matter which element you atomize first. You can atomize the sodium first, or you can atomize the fluorine first. Unlike ionization, where you need to oxidize the metal, then reduce the non-metal. So I'm going to start off by just working left to right. So I'm going to atomize the sodium to begin with. So I'm going to get my pen back up. So if I atomized sodium, it would go from sodium solid to Na as a gas. And that would be equivalent to the atomization of sodium. I'm not going to make any other changes. I make one change at a time. Like that. So we can see now the sodium's a gas. So now what we've got to do is look for an enthalpy change of atomization of sodium in my table over here. And you can see going from the solid to the gas, I've got this value here of plus 109. Being endothermic makes sense, you're breaking bonds. So I'm going to say that this value here is plus 109. Now I need to atomize my fluorine. So atomizing the fluorine will result in just fluorine atoms as a gas. So sodium gas goes to make fluorine F, just F, not F2 anymore, as a gas. Now that is actually balanced for that. However, we've got a slight issue in the value that's been given in the table, which is why I've really been emphasizing this point. If we look at the value in the table that results in the formation of fluorine atoms, we can see that we're actually provided here with a bond dissociation enthalpy, or a mean bond enthalpy. It's forming 2 fluorine atoms, whereas actually balancing for the formation of sodium fluoride, we only need to form 1 fluorine atom. So the value here is twice what we need, so we're going to need to halve this value when we use it. So actually I should be writing this value in here as the plus 158, but over 2. Because I'm only forming 1 atom of that fluorine, and I've not been provided with an enthalpy change of atomization, which would be that. I've been provided with a mean bond enthalpy. So now we can see that there's been a change between this new line that we've written and this upper line. We can see that the sodium is now a gaseous ion and its electron has been oxidized or removed from it. So this here is our first ionization energy of sodium. And we can see that we've got a value over here already for that of plus 494. So I'm going to put that in. Plus 494. There we go. Our next change, if we look between here and here, we can see that the electron that was oxidized or removed from that sodium atom in the previous stage is now paired up with the fluorine to make fluoride. And this tells us that the fluorine has undergone its first electron affinity. It doesn't need to undergo a second electron affinity, of course, because fluorine's group 7, so it only forms 1 minus ions. And we can see we've got a value here associated with the first electron affinity of fluorine to make fluoride of minus 348. So I'm going to add that now. Minus 348. Okay. So finally, we're asked to calculate the enthalpy of lattice formation. And this follows exactly the same method that we looked at previously. We've got root 1 here, all of this being root 2. So if I do this value minus the sum of all of the values that we know on the other root, I will get this value here. So my lattice enthalpy of formation, delta LEH or delta HLE, is going to be equal to minus 569, that's my root 1, my enthalpy change of formation, minus, open the brackets there, 109 plus 158 over 2 plus 494 minus the 348. Close my brackets, type all that into my calculator, put my answer over here. Let's see what we get. So I got a value here. Hopefully you've got the same. Please do practice typing this into your calculator. Don't just mindlessly watch and copy over the answers. I know the compulsion to do that. It's minus 903 kilojoules per mole for this particular example. Right, we're now asked how the lattice enthalpy of formation of sodium chloride compares with that of sodium fluoride. And when you're ever asked for a comparison of enthalpy, then what you need to do is you don't need to just say, is it larger or smaller? You actually need to say, is it more or less endothermic or exothermic? Right? So you need to say whether it's more or less endo or exo. That's how we word a comparison of enthalpy changes. Always more or less endo or exothermic. Now this is lattice formation. So lattice formation means going from like gaseous ions that are separated to our lovely solid ionic compound, right? Because it's formation. So plus, minus, so on and so forth. So what we're actually doing here is making bonds. And because we're making bonds, it's always exothermic. It releases energy. So actually in this case, we need to say whether it's more or less exothermic because we're making bonds. Now, what we need to do is think about how those bonds would be stronger or weaker in sodium chloride versus sodium fluoride. Okay, if they're stronger bonds, then more energy would be released, so it would be more exothermic. If they're weaker bonds, then less energy would be released on their formation, so it would be less exothermic. So let's consider sodium chloride versus sodium fluoride. Well, here's fluorine on the periodic table, and here's chlorine. So fluorine, being in a lower period, would be quite a small ion, right? Have quite a small ionic radius for a 1- charge. Whereas chlorine has a whole extra shell. So it's a much bigger ion, but it's got the same charge. So it's got a larger ionic radius. Now, if you've got a large radius but a 1- charge versus a small radius with a 1- charge, the one with the larger radius is actually going to experience less electrostatic attraction because there's more distance and more shielding between that charge and the nuclei of the adjacent atom. So actually, this sodium chloride that we see here is going to have weaker bonds, right? Weaker bonds because it's got a bigger chloride ion. Because it's got weaker bonds, it's going to be less exothermic. It's going to release less energy upon its formation. So for sodium chloride, it will be less exothermic. And the reasoning for this is that Cl- is a bigger ion. Right? Let's word that a bit better. Bigger ion, we could say larger ionic radius, for the same charge that is. Yeah? Larger ionic radius. So there's going to be less electrostatic attraction in that giant ionic lattice. If you've got a larger radius, you've got a worse charge density. So there's less electrostatic attraction, which results in weaker bonds. And there we go. Okay. Now, why did I talk about sodium chloride and not sodium fluoride? Because it asked me how the lattice enthalpy of formation of sodium chloride compares with that of sodium fluoride. So I'm going to talk about sodium chloride. Now, obviously, if you'd have talked about sodium fluoride, that would be fine if you were going for the inverse answer. But the standard one is going to be asking about how this one compares, with the other one. So you should really be talking about sodium chloride here. Okay, so a little bit more of a challenging question this time. It does link in a bit of AS knowledge, and actually we're asked here to calculate the volume of fluorine gas at these given temperatures and pressures in order to produce 1 gram of sodium fluoride by reaction with excess sodium. So this is a PV equals nRT calculation, and in order to do this, what we're going to need to do is calculate the number of moles of fluorine gas that need to react. So the way we're going to do this one is by writing an equation to begin with, so that we can relate the moles of fluorine to the moles of sodium fluoride. So to begin with, sodium as a solid will react with half a mole of fluorine gas, fluorine being F2, so therefore we need half of it, and that will produce 1 mole of NaF as a solid, that solid ionic compound there. Now we know that we've got 1 gram of this sodium fluoride, and we need to relate the moles of this sodium fluoride with the moles of fluorine that actually reacted. So we're going to need to do some reacting mass calculations. So we've got mass, MR, and mole. Okay, so the mass of sodium fluoride was 1.00 grams. And we're going to need to calculate its MR. Well, I've got 23 and 19 over here. Well, they add up to give an MR of 42 grams per mole. 42.0. Sorry, we do always need to write them to 1 decimal place. So in order to calculate moles, well, mole equals mass over MR. So I'm going to do the 1 divided by 42 like that. And then I'm going to get my moles. And my moles for this one are 0.02389, I think 5 that I got there. Yeah, that's about right. Okay, right, so now that we've got the moles of sodium fluoride, we'll be able to work out the moles of fluorine. Well, these are related by a 1-to-half relationship in the ratio of the equation. So if I halve this value here, I will get the moles of the fluorine. So I've got the moles of the fluorine to be 0.01190,476. So now that I have the moles of fluorine, I'll be able to calculate the volume of fluorine by using the equation PV equals nRT, rearranged for volume. So V would equal nRT over P. Well, I have that mole value now, so let's start working over here. So I've got volume is equal to N, the number of moles. Well, I've got 0.011904776 times the gas constant R, 8.31, times the temperature, which was 298 Kelvin. Now, that's already in Kelvin, but sometimes you do need to convert the value to Kelvin by adding 273 to it. We'll divide that by the pressure now. Notice how the pressure is in kilopascals. So I'm going to need to convert that to pascals. So it's 100 times 1000 to have that kilo prefix accounted for. So then I get a volume that comes out, in this case, as 2.948 times 10 to the minus 4. Now, very, very important. When you use PV equals nRT, that volume that you get is in meters cubed. And remember that 1 meter cubed is equal to 1 million, or 10 to the 6, centimeters cubed. Okay, so we need to now convert this answer in meters cubed to centimeters cubed. So what I'm going to do is times it by 1 million, times it by 10 to the 6. And when I do that, I get my volume in centimetres cubed. I get 294.8 centimetres cubed. And now finally, all I need to do is change this value so that it has the same number of significant figures as any value given in the question. And we can see that the number of significant figures in this question is 3. So actually that rounds to 295 centimetres cubed. Okay, another Born-Haber cycle now. So we've got the potassium oxide at the bottom here, and the first line should be our elements in their standard states balanced to give this product. So this one's K2O. So what I'm going to need is 2 potassium solid. It's only got 1 oxygen in it, so it's going to be plus a half O2 gas. So that there will balance to give that product. And we can see up in our table over here, this is an enthalpy change here of formation. So do we have that? Yes, we do. Minus 362. Next up, what I'm going to need to do is atomize step by step. So I'm going to first atomize the potassium. So I'll have 2K as a gas plus half O2 as a gas, because that hasn't changed yet. Now, very, very important. This is atomization, but look, we've formed 2 atoms. So when I look at the table over here, let's have a look for atomization of potassium, 90. Well, atomization always forms 1 atom. So what I need to do is actually double the value for atomization because I'm doing it twice. So this is going to be 2 times 90 here. Okay. Next up, we're going to need to atomize the oxygen. Okay. So I'll end up with 2K as a gas plus O as a gas. Okay. And if I look at my values that I've been provided with, now this time they've actually given us a proper atomization value for oxygen. It's not a bond dissociation enthalpy that forms 2 atoms, or a mean bond enthalpy that forms 2 atoms, because you're breaking 1 mole of bonds, and when you break a bond you form 2 atoms. This is just plain up good old atomization. So that is just forming 1 atom. Okay, so that value is good because we're only forming 1 atom. I don't need to double it. So I'll take this value here, atomization plus 248. Now let's have a look at what other values have changed. So we can see now that what we've done is we've formed potassium ions. Okay, 2K plus. Now because they're only +1 ions, this is only the first ionization enthalpy, but it's happening twice to form 2 ions of that. So actually what I need here is to take that value twice. So I'm going to do 2 times plus the ionisation enthalpy, which is 418. Right, next up, we can see that the oxygen has become a -1 ion. So this refers to the first electron affinity of oxygen. We're only doing this to one oxygen atom, so that only needs to happen once. Okay, so that's -142. Okay, next up, we can see that the oxygen has changed into an O2- ion. So this is now the second electron affinity of oxygen, always endothermic for your second electron affinities. So this one here is going to be +844. Now we didn't need to multiply these values because again we were only working with one atom or one ion of oxygen in these particular cases. Okay, so now that we've got all of our values, we should be able to calculate this value over here. Okay, so we should be able to calculate that. So our lattice enthalpy, delta LE, will be equal to -362 minus the sum of all of the values we know. So that's 2 times 90, put that in brackets, plus 248 plus 2 times 418 for that first ionisation energy, plus, well, not plus, but plus minus, same thing, 142 plus 844, and there we go. Now when we do this, let me just check my notes quickly. There we go. When we do this one, we get a value for the lattice enthalpy of -2,328. But that is not the answer to this question. Why? If you looked carefully, this arrow is going up. And actually in the question for this, it doesn't ask for the lattice enthalpy of formation. It asks for a different lattice enthalpy. It asks for the lattice enthalpy of dissociation. Now this is a different value. Formation is when you're going from the ions in their gaseous state to the ionic compound. That's formation. Dissociation is going back the other way. It's breaking the bonds. Now, luckily for us, this value is exactly the same. You just got to flip the sign. Forming the bonds would release energy, hence the negative here. But breaking the bonds would require energy. So all we need to do with this value here is flip the sign. Plus 2328, because the value is the arrow, is going the other way. So nice simple trick for those if you're asked for lattice enthalpy of dissociation versus lattice enthalpy of formation. Next up, we've got to explain why the lattice enthalpy of dissociation for potassium oxide is less endothermic than the one for sodium oxide. So let's get a good idea of what they're talking about here. So lattice dissociation, that means you're going from your lattice back to your gaseous ions. Completely separate. So it makes sense that they're endothermic because you'd need to put energy in for bond breaking. Okay. Now less endothermic, what less endothermic means is that the bonds are weaker. Requires less energy to break, right? Less endothermic. So it's basically saying, why are the bonds weaker in potassium oxide than they are in sodium oxide? Well, if we think about the ions involved, here's potassium, here's sodium. Both +1 ions, Na plus versus K plus. Well, because potassium has a whole extra shell than sodium, it's a bigger ion than sodium. Nice little small ion. Okay? So, therefore, the charge density of potassium is less than the charge density of sodium. It's a much larger ion in potassium. So it's going to have weaker electrostatic attraction. So we can say that the bonds in K2O are weaker as the electrostatic attraction is weaker because K plus is a bigger ion, larger ionic radius, than sodium. Okay, bigger ion, weaker attraction, simple rule. Okay, so that's how we would word that particular problem. Okay, thanks very much for watching that, guys. I hope you found it useful. What we're going to do now is plenty of practice on Born-Haber cycles and their associated questions. So as you can see there, the format of those questions is pretty much always the same. It's complete the Born-Haber cycle by adding the different symbols onto the lines, then do a calculation associated with that. As you can see, there are all sorts of like intricate things that you need to know with regards to multiplying some values, dividing other values. Hopefully that was a good overview of when to and not do that. But also then there's the accompanying questions that ask you whether a lattice enthalpy is more or less endothermic depending on the size of that ion there. So what I've done on Google Classroom is provided you with a set of additional practice questions following on from those that you've just seen in this video. So please complete the ones we've done in this video and then move on and have a look at having a go at those further questions to see how you cope with those. Practice with these is absolutely essential to mastering them. Once you get your head around it, it does actually become quite easy. So do just keep going at it and I'm sure you'll be all right. Thanks very much. See you next time.